All right, welcome. So in this video, I want to talk about the class of decidable languages. So far, we've been using very simple encodings to ask questions about numbers. And in our last video, we talked about maybe extending that. So we've been using unary, only zeros, right, to encode, say, a block of n zeros encodes the number n so that we can compare it to another block of zeros that encodes the number n squared. Well, we could have a very similar language where instead we encode them with binary. So in this case, I've just said maybe we have w and x, where w and x are binary numbers. So now they're written in binary, but x is equal to w squared. That would be the very similar language, but now the pattern of the string is much different. It turns out this one, if we can compute the first one with a Turing machine, we can compute this one as well. And of course, we can imagine extending this to decimal or other number systems as well. In these examples, we've been using an explicit encoding scheme, meaning we've been telling you we're using unary, or we're using binary, or we're using base 10, or whatever base we might be using to encode our numbers. As we start talking about Turing machines in more detail, we start realizing that we can encode numbers in many different ways, and we start being agnostic about what that encoding scheme is going to be. So we sort of leave it implicit instead of explicitly stated. When we do this, we like to use angle braces instead. So this would be a third version of our language where we say, okay, n and m, where n and m are numbers now. You notice I've changed it from w and x, which I was using for strings, to n and m, which we'll use for numbers. And all I said is they're numbers. I didn't say what kind: binary numbers, unary numbers, decimal numbers, whatever. They're just numbers. They're encoded. What we're saying here with the angle braces is that they've been encoded by some encoding scheme, but we're not going to tell you what that encoding scheme is. We'll leave that up to you to imagine what it is, or maybe design it yourself if you want to come up with it. That allows us to now encode all kinds of things. We don't have to go into a lot of detail. So for instance, in language 4 here, I've encoded a set and maybe a member of that set. And I'm just saying S is a set and little s is a member of S. Okay, that's the set membership problem basically. Okay, we could also have this language here where G is a connected graph. So this is some kind of graph that's been encoded, and we want to check to see if it's connected. We could ask questions about DFAs. DFAs are graphs, for instance. So we could say D is a DFA and W is a string, and D accepts W. And D accepts W. These are all languages of complex mathematical objects that we can imagine can be encoded in some way, and then we could ask questions about them. So this allows us to extend the languages that we've been doing from just strings of like binary strings into graphs and sets and other things that we're interested in. We've already extended into numbers, but now we can go deeper into the mathematical world, and any mathematical object that can be well defined then can be encoded. Let's explore this a little bit by looking at encoding a DFA, something we might want to given this series of videos. So remember, first of all, that a DFA, we said formally can be defined in this way. Now this is one of the reasons why we wanted to have formal definitions of DFAs. Yes, they were helpful in our proofs, because then we could say, yeah, we have a DFA and it looks like this, and then we'd prove something about Q or sigma or whatever. But it's also going to be helpful now for us for encoding. We say, look, we can write any DFA down as a string over some symbols. In fact, here I've written a very explicit string over symbols. They're weird symbols. I've got deltas and sigmas in there, okay? But this encoding here encodes this DFA. So of course, our human brains like this pictorial depiction. This lets us understand the DFA better, but in formal mathematics and in computers, a formal definition like this is more useful. So we could encode our DFA as a string in this way. Now this is a string over a pretty complicated alphabet. This alphabet has open braces, open brackets, Q, sigma, delta, 0, 1, and a comma in there as well. So this is a pretty complicated alphabet. We might say, hey, the language that I'm computing on is not over this alphabet. It has to be over the binary alphabet. Okay, no problem. We can actually encode any alphabet into binary as needed by using a set of what we will call code words, okay, and explore this a little bit more in encoding theory, okay. For instance, encryption is a place where we might use encoding theory like this, or compression, okay, where we might use this. And I have a few videos of those in my data structures series if you want to explore that a little bit more. But this is a very simple example. So we might go ahead and say, okay, I'm going to encode 0 as 4 zeros and 1 as 4 ones. I'm using 4 binary bits here because I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 symbols I need to encode. And if I do the ceiling of log base 10, I will get 4. That tells me how many bits I need to encode those symbols. So I need 4 bits. Of course, you could just try it out too. You start with 0. Usually you do 0 then 1. I picked all ones here for 1 because that's just sort of an easy way to encode all ones. And then I just started going through my numbers. This is 1, that'll be open bracket, 2, that'll be close bracket, 3, that'll be close bracket on this side. So I got those backwards, close, open. 4, 5, 6, 7, and 8. Each of these in binary encodes a particular symbol. Turns out I'm not using the encoded strings for 9 up to 14. That's fine. Guess I don't need them. If I could add a few extra symbols if I wanted to, okay? But if I've done this now, I can encode my all of these symbols in binary, meaning I can encode this DFA now in binary if I wanted to. So we're going to assume then that any well-defined mathematical object like our DFA can be written as a string of symbols as needed, whatever symbols, and ultimately we can encode these in any alphabet we want. And that might be the binary alphabet in a lot of the examples we're using. In addition, any of these encoded objects can be decoded by a Turing machine, meaning a Turing machine can read it and know what it means. So if we encode a DFA and we say, okay, the Turing machine is going to go see, look up this state in the transition function, it can decode it and know what the state looks like in the transition function. So some of the encoding schemes that you come up with are going to be both one-to-one and onto. And remember, that creates what we call a bijection, or a kind of function where we've paired numbers together with, or objects together with their strings, meaning every object has exactly one string and every string has exactly one object. Okay, if that's the case, we've got a very special case where every string encodes a DFA, or every string encodes a number. Okay, but that's not always going to be true. Certainly not in the encoding scheme that we just came up with. That was not true, but it can be the case. And if we want it to be the case, we can force it to be the case, but it's not always going to be the case. So what that means is sometimes we could have an input string that does not properly encode a DFA at all. It's just gobbledygook, it's just garbage, it's just gibberish. In that case, we can also assume that if you give us input that does not properly encode what we're looking for, we immediately reject it. And by immediately, I mean we don't do it in one step. It just means we scan over it, we make sure it's properly well formed, and if it's not well formed, we can just reject it. And so any Turing machine that is taking an encoded string as input, we can always assume that that is properly well formed, and we reject otherwise. So what that means is we can start defining languages like this. And I'm going to call this ADFA for accept DFA. So this language will detect if the input DFA D accepts the input string W. And again, here W, I've got it inside these angle braces to indicate that W might be encoded as well. W might be over a different alphabet than the alphabet that this language is over. And again, if we're just assuming this is over the binary alphabet, W might need to be encoded in binary as well, using the same strategy that we just followed. What I want to show is that this language is actually a decidable language, meaning we can build a Turing machine that actually decides this. Now to do that, we're going to have to use pseudocode. So I've got a pseudocode description here. And to do that, we're going to actually have to operate at a fairly high level using some of the assumptions that I just indicated we could. Meaning that in this encoding of a DFA, one of the things we can do is scan over it and find, for instance, the initial state. Okay, so what we're going to do is I'm going to show how we're going to construct a Turing machine that does this. This is going to technically be a K-tape Turing machine. Okay, the first thing we're going to do is we're going to find what the initial state is, and we're going to write it on our second tape. We're just going to use the second tape here to keep track of what state we're in. Okay, we're going to scan the current symbol of the input, and we're going to go look up the current state on the second tape, and then we're going to go look up in our transition function, and we're going to find out what that next state should be given that combination. Given what that next state should be, we're going to go and update the current state on tape 2 so that it now indicates that we're in that next state, and then we're going to move our tape head over to the next symbol of the input so that we're scanning the second symbol. We're going to repeat this now. Go back and do it again. Go check the current state, the current symbol, and go to the transition function and figure out the next state. So we'll keep doing this. We're basically simulating the DFA, figuring out what each of its next states is until we get to the end of all of our symbols. And then we're just going to see, are we in an accept state? If so, we accept. Otherwise, we reject. So very straightforwardly, as long as we can encode DFAs as strings, we can describe a Turing machine that basically is going to be scanning over that DFA over and over again to find out what state we're in while keeping track of its state on tape 2, eventually carrying out the whole simulation of the DFA. What does that mean? This language, a DFA, must be a decidable language. As sort of a side effect, we can use that to show that any DFA can be simulated by a Turing machine, so the regular languages must be decidable, something we probably already knew. Okay. Another thing we could say is we could call this Turing machine the universal DFA. What that means is it can take any DFA as input and simulate it. It doesn't just simulate one DFA, it simulates all the DFAs. It can simulate every single one. Pretty cool, okay? All right, we'll keep this going. We can take this machine that we've just built and use it to show that other languages that we might care about are also decidable. So here's another interesting one. Let's call this a NFA. Same definition, except that now we've encoded a non-deterministic finite automata, and we still want to know, hey, does that accept this string W? Okay. We could try and simulate it, do a breadth first search like we saw in our earlier video about simulating, a non-deterministic Turing machine, but we don't need to do that because what we can do instead is rely on some of the proofs and the constructions that we've already laid out. So here's an example. We're going to, same thing as before, we're going to build a machine, but we're going to now use the fact that we can convert a NFA into a DFA as an algorithm as a subroutine. We're basically going to say, hey, we could define a Turing machine that takes any encoding of a NFA and converts it into a DFA and then writes down that encoding of the DFA instead. So that's the first thing we're going to do. We're going to take our NFA and convert it to a DFA, and then we're just going to use that machine we already built. We're going to simulate it on our encoding of a DFA with our string W and just do what it does. Same thing as before. If it ends in accept, we accept, otherwise we reject. So basically we're nesting subroutines inside of our machines now in a way that we're basically building procedural computation into our Turing machines. So can we do that also with regular expressions? For sure, because we also know that regular expressions can be converted into NFAs. So we can we could do this in 2 steps if we wanted. We could say convert into an NFA and then convert that NFA into a DFA and use M1, but we already have M2. So we could just say convert it into an NFA and use M2, which we know is about to go convert it into a DFA and then use M1. So we've now got a nested 3 machines to make this work. Again, showing that we've now got a universal DFA, a universal NFA, and a universal regular expression, all that we could build into a Turing machine. Okay, what about some other interesting languages? So maybe we want to see if a DFA accepts no strings, or alternatively, all of the strings. In this case, we could say, how would we build a machine that does that? Well, can we use one of those other machines? Maybe there might be a clever way to do that. I'm not exactly sure. But instead, what I'm going to do, at least in this proof, I'm going to just do it directly. What I'm going to try and do is see if there's any way to reach an accept state. If there's any way to reach an accept state, then I will be accepting in a string, so I should not, I should reject in this case. So how do I do that? Well, I'll start by marking the start state, and I'm basically just traversing the graph. So I'm going to mark any other state that has an incoming transition from a marked state. So initially that will be mark any state you can get to in one step from the start state. But I'm going to repeat steps 2 until there's no new states marked. So I'll just keep branching out, marking every state that I can reach. So at the end of this, every state that is reachable will be marked. If an accept state is in that set, then that means we accept some strings, so we should reject. Otherwise, we'll accept. So this is a way of just showing that we can also check to see interesting properties about these machines. So not just if they accept or reject strings, but do they accept or reject all the strings or none of the strings? That's like running the machine on infinite strings, okay, in some sense. We haven't, but it's like that because we've answered the question for all infinite strings. Now, interestingly, I haven't done this one, but I want to pose it as a quick little exercise. What if we wanted all DFA? That is the opposite of that. It accepts all the strings. We could do exactly the same pattern here, except, look for regex states, make sure we hit only regex states. But I think another interesting way we could do this is by using M4. And the way we could do that is by taking the DFA, flipping its accept and reject states, so that we're effectively making it do the search with rejects instead of accepts. Okay, and again, if we do that, we can show that all DFA, again, leave that as an exercise, all DFA is also a decidable language. Okay, here's another interesting question we could ask about 2 DFAs. This is actually a useful question. For a particular language, there is typically more than one way to design a DFA for that language. Okay, now what that means is there could potentially be infinite DFAs for a single language. And we might want to grab 2 DFAs and be able to tell if they have the same language or not. And that's what this particular language is asking. If I've got 2 DFAs, can you tell if they have the same language? So sure enough, we should be able to do that, and we're going to be able to do that by using our previous machine. Now this uses an interesting idea. It's going to use the idea that if you take a machine and you intersect it with the complement of the other machine, then you should be empty. Okay, let's go through this idea for a second. If they have the exact same language, right? If we have the exact same language and we intersect them, we get the exact same language back, right? But if I have the 2 languages and I intersect one with the complement, then you should get nothing back if they're the same language, okay? So if I do that, this is basically saying, are there any strings in D1 that are not in D2? If there are, they would show up here. If not, this would be empty. And then we do the same thing for the other pairing. Are there any strings in D2 that are not in D1? If so, they would show up in this pairing. Then we union those 2 together, because we want to see if there's any of those. And we'll call this the language of D3. So we're going to write down a D3. We're going to use the fact that regular languages are closed under complement, union, and intersection here to confirm that we know that from these first 2, D1 and D2, we can always convert and draw a D3 to know that we can write down this description of D3, and then we will run M4 on D3. Now remember, what M4 does is it checks to see if D3 is empty. So if this is empty, that means there were no of these special strings that were not included in the other language. So they must have been the same language, so we should accept. So if M4 accepts, we accept. Otherwise, we reject. Again, this shows us that EQDFA, checking to see if 2 DFAs are the same, is a decidable language, something a Turing machine can do, meaning something a computer can do. Okay, let's switch to the context-free languages. We've been talking about regular languages. It seems like there's lots of interesting properties of regular languages that we can compute with the Turing machine. What about context-free languages? Can we make a universal context-free grammar, something that takes a description of a grammar and a string and tells us that that grammar decides whether it can generate that string or not. Okay, now in this particular one, there's a reason why we had to talk about Chomsky normal form. I mentioned it was going to be useful in some proofs. It's also useful in some computations. There's actually a property of Chomsky normal form that's actually useful here, which is if you have any grammar G that's in Chomsky normal form, and you're deriving some string W that can be derived with that grammar, if W is of length n, the derivation using that grammar will have at most 2n minus 1, and that's because of the structure of the grammar that's guaranteed. Okay, so what that means is, in this normal form, we know that derivations of strings have a specific length, which means we can track down that particular derivation by just looking for all derivations of that length. And that's what we're going to be doing. So first thing we're going to do, we've got our input grammar. We don't know that it's in Chomsky normal form, but we know we can convert it to Chomsky normal form. So we're going to convert it to Chomsky normal form. Then what we're going to do is we're going to list all the derivations with length, well, up to 2n minus 1. Now only one that doesn't work for is n equals 0. Now let's think about what that means. If n equals 0, that means the length of our input string W is 0. That means our input string is epsilon. That means we're looking to see if it derives epsilon. Well, in Chomsky normal form, the only way you can derive epsilon is if your start rule says start rule goes to epsilon. So that's why it's saying any derivations with length 1, one of them should include the derivation for the empty string if it exists. So that's if n equals 0. Otherwise, what we're going to do is we're going to list out all derivations with 2n minus 1 steps. So that means we're going to write out a whole bunch of derivations. That might be a whole bunch, okay, an exponential number. But we're going to write them all down, and we're going to just check to see if any one of them is W. And if any one is, we accept, otherwise we reject. So again, this one's relying on the idea that Chomsky normal form can be written, or that derivations in Chomsky normal form have a specific length, and that every grammar can be written in Chomsky normal form. It makes this proof smoother because otherwise it's going to be hard to figure out the derivations, especially in cases where we might get into infinite loops. It's possible that we might be able to make a proof that goes that direction, but using Chomsky normal form, we can do this even easier. Okay, what about empty CFG or eCFG here? Can we detect that it generates no strings? Okay, now actually this might be kind of easy for a human to do, because usually what that means is the grammar consists only of a loop, like S goes to S, in some way that it generates nothing at all. And there obviously can be complex way that you can have loops that are not immediately detectable by humans. But if we were doing a human to detect this, we'd probably just be like, hey, is this only a loop? But we want to encode that idea in our machine here. Is this only a loop? Or the other way around maybe being, is this not only a loop? Is there a way to get out of the loop and eventually arrive at a terminal? And that's how we're going to do it. It's a similar idea to what we did with our DFAs and marking states. We're going to be marking variables, but we're going to start by marking all the terminal symbols in G. So anywhere in our grammar where there's a terminal, we'll mark it. Then what we're going to do is we're going to look for variables A on the left-hand side, where on the right-hand side, all the symbols are marked. So if we had a symbol that if we had a variable that just went to a terminal, we can now mark that variable. And then we're going to repeat this. So now we can mark more variables and more variables. We'll keep doing this until no new variables are marked. So we've marked every variable that can be marked in this way. If we can get back to the start symbol, then what we've basically done is backtracked through a path that ended in all terminals and started at the start symbol, because we backtracked all the way to the start symbol. So if we can start at the start symbol and get to all terminals, then we can generate a string. So if the start symbol is not marked, then we should accept, meaning we generate no symbols. There's only a loop there. Otherwise, we reject. Okay, so that will help us detect to see if a context-free grammar is empty or generates no strings. Okay, and again, we might be able to use this to show that other languages are decidable as well. But again, the goal of this here is just to show that some properties of context-free languages can also be detected, or context-free grammars in this case, can also be detected by Turing machines. So that leaves us with an interesting conclusion here, which is that we've just shown in one of our previous cases here that we have a universal context-free grammar. If we have a universal context-free grammar, then that means every context-free language must be decidable, because we can certainly make a specific context-free grammar. We can simulate a specific context-free grammar. That's all I'm going to be showing out here. Is I'm going to say, hey, say we've got some specific grammar G. We can actually use our universal machine M6 here. We can just take our input W that's coming in. If we want to simulate G, the first thing we'll do is write down an encoding of G and then just use our universal grammar machine to simulate it. So what that allows us to do is complete an interesting picture that we've sort of been drawing for through this entire series of videos, which is a hierarchy of sets of languages that can be computed. We can think of this also as a hierarchy of computational models. We have at the heart, at the center, are DFAs, just our finite automatas that define the regular languages. Then pushing out from there, we have context-free grammars and DFAs with a stack as extra memory, defining the context-free languages. That's sort of an interesting intermediate set of languages between the regular languages that we use quite a lot and the decidable languages, another set of languages that are Turing-Decidable, meaning all those languages that can have their membership be accepted, but also non-membership be rejected by a Turing machine. And then outside of that, an even larger set of languages, the Turing-recognizable languages. Those are the ones that can have their membership accepted, but possibly not reject the non-members, maybe run forever on the non-members. That's the largest set that I've got depicted here, but there's an even larger set out here, the whole universe of languages that include languages that are not decidable and not recognizable. And that's going to be beyond the scope of this video. So I'm going to thank you for watching this video. And in that next video, we might explore non-decidable and non-recognizable languages. Thanks a lot for watching, and we'll see you in that next video.